To get us started, just to make sure everyone is on the same page, perhaps as an opening question, we should ask what exactly is dark matter and why is it such an interesting topic? And to get us started, who better than the instructor of the Astronomy 101 course at the University of Toronto, Professor Webb. Can you give us quickly a reminder of what dark matter actually is?
Well, it's an interesting question because we don't actually know what dark matter is. To phrase it like that, I can't answer that question. That would be a pretty big deal. But I guess the problem of dark matter, or the issue of dark matter, is that when we observe galaxies and galaxy clusters out in the universe, we can measure things like measure their properties, like their mass and how fast objects are moving in those galaxies. And there's the earlies back at the 30s, and then a lot later in the 60s and 70s, all this observational evidence came in telling us that galaxies were very massive, significantly more massive than what you would see with your eye or in a telescope. So if you try to add up all the stars in a galaxy or add up all the gas in a galaxy, it's just a small fraction of what the mass you believe it to be. And so this led to astronomers and physicists coming up with this idea that there's some missing mass in the universe. There's something out there that we can't see that's contributing to galaxies being this massive. And we just simply called it dark matter because we can't see it. And so the term dark just comes from the fact that it doesn't interact with light, but we believe it to interact gravitationally with the universe around it.
Thank you. So a reminder that you can ask your questions in the Q&A tab at the bottom of your screen. In the meantime, you mentioned that dark matter doesn't interact with light, and so it interacts mostly only gravitationally. And so the question that comes to mind is, how can we hope to detect it one day? So how can we build a detector to try and capture and then observe that dark matter particle? Perhaps Professor Diamond, who's worked on detectors, could enlighten us on this issue.
Sure. So when we say that the dark matter does not interact with light, we technically mean that it does not interact with photons, which are the carriers of the electromagnetic force. There are four forces. As well as electromagnetism and gravity, there's the weak force and the strong force. And we had, up until a few decades ago, actually our leading idea was that the dark matter particles perhaps also interacted via the weak force. We now have had several generations of experiments basically looking for a new type of subatomic particle that has a weak force charge. And we initially thought that neutrinos might be dark matter. You can actually think of neutrinos as a type of dark matter, just not the dominant type of dark matter in the universe. And so we were looking for some sort of similar particle, which we called a weakly interacting massive particle, or WIMP. So if you put aside the humor of the acronym, WIMPs were a serious dark matter candidate, and still WIMPs or WIMP-like particles are a possibility, but we don't think that they do interact via the weak force. We think that there may be some new force of nature, which we have not yet discovered, which would be literally the dark force, and it would have a carrier particle like a dark photon, which would, yes, be the dark side of the force. We have some other options for what we call portals from the standard model to the dark sector, which is basically possible, very feeble forms of non-gravitational interaction that have not yet been ruled out. So most of our detectors, and there's many different types of detectors that are optimized for different types of portals and different masses of dark matter particles, are looking for these extra forces or mediators. as a particle physicist, my worst nightmare actually is that dark matter turns out to only interact gravitationally, because then it's extremely difficult to see it in a particle physics lab, just because the gravitational pull of any subatomic particle individually is absolutely infinitesimal. And then even of what by Earth standards is considered a fairly large collection of particles is really on the cosmic scale also pretty minuscule. So then I would have to sort of sit back and let the astrophysicists have most of the fun with large gravitationally bound objects. And so I'm really hoping for something exciting, like some new beyond the standard model dark force.
Thank you. And I noticed that in my question there was an assumption that one of our attendees spotted. So I assumed in my question that the dark matter was a particle. So perhaps I can direct this question to Professor Cline, who's also worked in particle physics. What evidence do we have that dark matter is a particle?
We have absolutely no evidence that it's a particle, although I would say it's more likely that it's a particle. Ever since LIGO made its very striking observations of black hole mergers, and so more proof that there are black holes out there in the universe, people have been talking about black holes as a possible dark matter candidate. And it turns out there's so many astrophysical constraints on black holes that there are only very narrow little windows of black hole mass where they could be even appreciable fraction of all the dark matter. There's also the possibility that dark matter is, even if it's a particle, it might be a particle that likes to clump together into big clumps. And so people have written about that possibility. And so in that case, you would say, well, it's not an elementary particle. It's like a asteroid size or something. So it's possible, but you have to do special, in all of these cases, you have to do special things to make that happen. Whereas if it's just an elementary particle, that's like a very generic possibility. And since that's the simplest thing, we like to use Occam's razor in science. We like to test the simplest possibilities first off. And there are many theoretical proposals for what kind of particles dark matter could be.
Thank you. So I'm just going through the Q&A. So we had a question right before the start of the event in the chat, which I'm going to open the floor for all three panelists if you want to chime into this question. Our viewer asked, will we ever be able to see what's on the other side of the visible universe? This is a question more about general cosmology, but can we ever hope to see beyond our visible universe?
I could jump in there. That's a very interesting question. So what is the edge of the visible universe? It's something we call the surface of last scattering, which represents the moment of time when the universe became transparent to photons. That is when electrons and protons recombined to become neutral atoms. Then photons could move freely without being appreciably deflected. So if we look out in the universe and look at those first photons that were free to travel, that's the cosmic microwave background. And so we're seeing that surface in the cosmic microwave background, and that's as far back as we can see using light. On the other hand, the possibility that gravity waves could be coming from even farther and probing back to earlier times in the universe. And so this is actually one of the holy grails of experiments that are looking for gravity waves, like the LIGO experiment, but probably they won't be able to see those cosmological gravitons. Whereas upcoming experiments, there's the LISA experiment. Don't hold your breath, it's going to be in 2030s, but eventually, we will have experiments that are able to probe gravity waves in that frequency range that we expect from the extremely early universe. People are very excited about that in physics.
Yeah, scientific experiments often take a very long time to complete and build.
Yeah, this one is basically three observatories orbiting around the Earth, and so it's quite a technological feat.
Exactly. Thank you. Speaking of detectors and experiments, one of our viewers asked, what is a neutrino? So that particle came up earlier in the discussion, and so they would like to know a bit more about the neutrino particle.
So I guess that would be me. I actually started my career working on neutrino physics for the Sudbury Neutrino Observatory project. You may remember that the director of that project, Dr. Art McDonald, was one of the Nobel laureates in physics a few years ago. And neutrinos are actually a very interesting story, especially to give us perspective on the current dark matter searches. When the neutrino was initially proposed, it was essentially a solution to a missing energy problem. And so people noticed that when a neutron decayed into a proton and an electron, they thought that this was just a simple two-body decay, and that therefore they should be able to predict how much energy each of these bodies would come out with. And instead, looking at the energy spectra of the outgoing electrons, they realized some energy had gone missing. And so there was one possibility, which was that conservation of energy did not actually hold in fundamental physical laws. I think it's sort of similar to the suggestion now that maybe the laws of gravity don't hold over sort of cosmological scales, and that maybe we need a fundamental modified gravity theory. So the idea of some particle running away with some energy was initially criticized by some scientists as, great, you're predicting a particle that we can never actually observe because you're saying it's invisible and none of our experiments can pick it up. It was called the neutrino, short for little neutral one. We now know that there are actually three different flavors of neutrinos. There's the electron, muon, and tau neutrino, and they can oscillate spontaneously between those flavors. So as they're traveling along in the vacuum, they suddenly just decide, poof, I'm gonna turn into a different flavor. And the Sudbury Neutrino Observatory experiment found essentially evidence of these neutrino oscillations by looking at neutrinos that were produced in the core of the sun through fusion reactions and that are raining down on us all the time. So there's trillions and trillions of neutrinos going through every square centimeter of your body right now. You just literally are completely unaware of them because they go right through you without interacting. They can go through about a light year of lead without leaving a trace of their existence. So they are very mysterious particles in a lot of ways, but we've made a lot of progress in building detectors sensitive enough to find them using their weak force interactions. We can sort of use that as a model for building dark matter detectors now, because a lot of the same detection principles apply. We need very sensitive, very low noise, and rather creative detection schemes.
This gives us hope to detect the dark matter particle one day. If it is a particle, indeed, it might not be. There's a question in the chat about the spatial distribution of dark matter, so the way that it clumps. And the attendee asks about the distribution of dark matter on various scales, so the inside of galaxies all the way to galaxy clusters. So given research areas, I feel like Professor Webb that would be exactly in your field of expertise. So can you enlighten us on how dark matter clumps inside galaxies and galaxy clusters?
Yeah, absolutely. And that's a great question. So let's start on the smaller scale within a galaxy. So an individual galaxy is kind of believed to form within kind of a deep gravitational well that's caused by dark matter. So when you asked me about what is dark matter, I actually kind of failed to mention that not only is it something that we don't know exists, but it's the dominant form of matter in the universe. Right, so 60, 70, 75% of matter is this stuff we can't see, that we don't know about. That's not including dark energy. That's a different discussion. But just in terms of matter, it's the dominant form. So if you're thinking of a galaxy forming in a deep gravitational well, most of that gravity is due to the presence of dark matter. And so when you have a galaxy forming, all the stuff that we can see, all the gas, all the stars, all the what we call baryonic matter, all that stuff is getting drawn into the galaxy due to this background dark matter potential well. And so the galaxy is forming kind of in the inner parts of that potential well, but the dark matter itself can actually extend quite a bit farther out. So to kind of give you a rough scale, for the Milky Way, our own galaxy, we think the dark matter probably extends up to 3 or 4 times the distance that kind of baryonic matter stops. So we can see stars and star clusters out to a little beyond 100 kiloparsecs, but dark matter likely extends much farther than that, 300 or 400 kiloparsecs. But it's not believed to be smoothly distributed in a galaxy, which I think was also part of the question. And I think Jim mentioned this a little bit too. There's this question to how much does dark matter clump together? So it essentially we don't know, but kind of leading theories are suggesting that it does clump together a little bit, and so you kind of have these little mini clumps of dark matter orbiting around within a galaxy. Potentially, some of those end up forming mini dwarf galaxies or satellite galaxies that we observe. So kind of mini dark matter halos around the halo of the Milky Way. Some of those might be much smaller and just can't see them, but they're just kind of orbiting around in the Milky Way. So there's some degree of clumpiness, and that's a really active area of research right now, is how clumpy is dark matter? How many of these massive dark matter clumps do we expect to see in the Milky Way? And then when you extend that out to galaxy clusters, again, the dark matter just kind of keeps on going. And so when you have a galaxy cluster, which could be tens of galaxies, hundreds of galaxies, there's still this underlying massive dark matter potential well that everything's kind of in. That's the underlying galaxy cluster. And we've been able to infer its existence by how dark matter bends light. So when I said before it doesn't interact with light, and Miriam kind of clarified that, dark matter is not absorbing and emitting light, but dark matter is still warping space-time. And so it can actually bend the trajectory of light. And we call this, you can get gravitational lensing. And so we can measure how much galaxy clusters bend light. And that tells us that the dark matter in galaxy clusters extends out to very large distances, well beyond where we're actually observing visible galaxies.
Very interesting, thank you. So the dark matter goes way beyond the disk of the galaxy.
Yeah, definitely, most likely, yes.
And we had 2 questions actually about the interplay between baryons and dark matter. So the first question asks, can dark matter contribute to black hole formation? And can it contribute to star formation? So can it help some of the processes that are going on inside the galaxy?
I actually wrote a paper about the black hole question, so maybe I could chime in there. I think the answer is that probably it doesn't, but it might, and it depends on the specific properties of dark matter. And the reason we got interested in this question is because there's actually a quite interesting puzzle in cosmology right now concerning supermassive black holes of size, I think 10 to the 8th, 10 to the 10 solar masses. And the puzzle is that people are seeing them at very high redshifts, like Z equals 6. So that's when the universe was 6 times or 7 times smaller than it is right now. And that's very early when structures were just starting to form. And so people found it quite surprising that black holes that big could have formed so early. And so the quest was on for explanations. And one explanation we came up with is that it's possible that if dark matter interacts, even though we know dark matter interacts very weakly with ordinary matter, it's possible that it interacts quite strongly with itself. And in that case, it might fall into the centers of some of these proto-galaxies and cause a very sudden buildup of density that could stimulate the growth, the early growth of these black holes. So that's one example. And one other example that people have talked about is it's possible that dark matter could accumulate in the centers of neutron stars. It turns out if it's a bosonic dark matter particle, then this is much more important. And if that happens, then over time, you could accumulate so much that it would cause gravitational collapse into a black hole in the center of the neutron star and consume the neutron star. And the fact that we don't see a deficit of neutron stars compared to predictions leads us to put constraints on the interactions of such dark matter with ordinary matter, which actually are much stronger than the constraints we can get through the underground direct detection experiments for some of these dark matter candidates. So there's a couple examples where it could stimulate black hole growth.
Thank you. And that's a very interesting comments about how different approaches are complementary to each other when studying either astrophysics or direct detection experiments. So we have a question here about regions of the universe and the content that they have. So we know that baryons and dark matter can be in the same regions, but the attendee asks, can region of the universe have only dark matter and others have only ordinary matter? Or are they always clumped together? Do they always come in a pair?
I can try and tackle that a little bit. And that's to say, leading back to one of my earlier answer, you know, it's a lot more likely that dark matter can exist where there's no baryonic matter, right? It's a very massive or a very major component of our universe, major component of galaxies, and the fact that it can extend so much farther out than the visible part of a galaxy. You can definitely have regions in the universe where you're really only seeing high dark matter density and very low or negligible baryonic density. In terms of the other way around, so one of the things that I research the most are star clusters. You know, so these large sphere collections of stars. They can be hundreds of stars, thousands, millions, and they're kind of considered to be devoid of dark matter in the sense that there's no strong local density there. They didn't require dark matter to form. They don't require dark matter to kind of evolve, but they still have to form inside of a galaxy, and the galaxy needed dark matter to form in the first place. So it's not forming in a region where there's no dark matter, but dark matter didn't play a role in its formation and existence, only in the sense that it's orbiting the galaxy and the galaxy contains dark matter. So I think that's kind of the two sides of that answer.
Thank you. And the University of Toronto is also at the forefront of this dark matter and baryon question. If we remember the discovery of a dark matter only or very strongly dominated galaxy by the Dragonfly team, that's an example of a dark matter only region. Or there was also a galaxy not long ago that seemed to have very little dark matter. So that seems to contribute to what you were saying. Oh, and we have a question building onto that, which is, what do we mean when we say baryonic matter? So perhaps it would be good to refresh our audience on that as well. That is a very good question.
Okay. So that goes back to the standard model of particle physics. And this is our current best understanding of all of the fundamental building blocks of the universe and their interactions with each other. And it includes 6 different flavors of quarks. And so baryons are essentially particles that are made up of quarks stuck together. And specifically 3 quarks make a baryon. And when we sort of look around us at what we call ordinary matter, almost everything is composed of protons and neutrons, which is up quarks and down quarks stuck together. There are also electrons, but they do not contribute very much mass. So the quarks are the far more massive constituent of ordinary matter. And so when we say non-baryonic, we're looking for some beyond the standard model particle, usually.
So interesting, it would raise new physics to solve the problem. That must be an interesting playground for physicists. Now we have a question about the interaction between baryons and dark matter building onto that, which is dark matter interacts gravitationally with ordinary matter, but does ordinary matter influence dark matter gravitationally or through other ways? So when we're talking about the clumpiness of dark matter in galaxies, is that affected by when baryons are around? Does baryons also have an effect on dark matter?
Yes, absolutely it does. You know, at the end of the day, gravity is gravity, whether you're a baryonic matter or dark matter. And this is a leading issue in when we're doing theoretical studies of dark matter, because we're really computationally limited by how many particles you can throw in a simulation. And so for the longest time, we were just able to run dark matter only simulations. So every particle in your simulation is dark matter, and you don't worry about what baryons do. And we use these to kind of make predictions of the properties of dark matter. How clumpy is it? You know, how big or how massive could these clumpy little mini halos get? But it's only maybe been recently in the last 10-ish or so years that computers have advanced to the point where we can now start throwing in baryonic matter into these kind of simulations. And so an example would be, well, what happens if you have a galactic disk, right? So the Milky Way has this nice thin disk of stars in it and gas. And well, what happens when some of these little clumpy dark matter halos pass through that disk? Because all of a sudden, this little dark matter subhalo is passing into a region where the baryonic density is quite high. And this actually contributes to these clumpy subhalos breaking up. You get this, what we call a tidal shock, so an injection of energy, because the local density is increased so much. You inject energy into one of these dark matter subhalos, and they can actually break up. And so you can kind of picture that in regions of the galaxy where there's a lot of baryonic matter, so anywhere near the disk or in the inner regions, gravity from baryons has likely ripped apart a lot of the dark matter subhalos. And so if there's this degree of clumpiness, it's most likely in the outer regions of a galaxy where there's less baryons to break up subhalos. So great question.
So from my point of view as a particle physicist, I also think about, you know, what happens if there is some sort of a portal between the standard model and the dark sector. And that interaction does have to be very, very feeble, but there are some circumstances in which you could have a process where you start with standard model stuff and you end up producing dark matter stuff. In a supernova, for example, when a star collapses on itself, it actually releases something like 99% of its energy in neutrinos. So there are some models in which, you know, there's a similar process where you can spit out huge amounts of dark matter particles. If you apply a magnetic field to photons, for example, you can turn some of them into axions, which are a potential dark matter candidate. So there are possibilities for certain rather exotic processes where we might hope to see some sort of jet or some sort of collection of dark matter getting spewed out because of interactions with standard model particles.
Oh, that's a very interesting research avenue. It would be another interaction of baryons and dark matter. One of our attendee asks about computer simulation, which we mentioned a bit before. So what is the role of computer simulations in the study of dark matter?
Go ahead, Jim.
Yeah, probably both of us have things to say about that, but gravitational simulations are essential for telling us what we expect the dark matter distribution to look like in the universe and within the galaxy. And in fact, it's led to some really interesting problems when you do the most naive, or let's say the simplest simulations with only including gravitational effects. It tends to predict that the distribution to dark matter is too spiky in the center of galaxies compared to what's observed. And so that might be cured by putting in the baryonic physics. I think that's still, and maybe Jeremy will be able to elaborate on that. I think that's still an unsettled question. But one thing it has inspired is this issue that I was mentioning before of dark matter self-interactions, because another thing that can happen is that dark matter scatters with itself, and it actually scatters the excess density out of the center of the galaxy to reduce that spikiness. And so that's just an example of where these gravitational computational simulations has been playing a very important role in research in dark matter.
Yeah, so I was actually thinking a larger scale than the center of galaxies. And yeah, you're entirely right. I think that issue of the central dark matter density in galaxies is still pretty much an open question. But I was actually thinking in terms of large scale structure in the universe. So that's another thing these really gravity only dark matter simulations try to do, is you kind of pick your favorite recipe for what you think dark matter might be in terms of kind of its mass, its kinematic properties. And then you say, if a whole galaxy or a whole universe is made of that, what's the distribution of galaxies that form out of that? You know, do you get a large galaxy clusters? Do you get a lot of individual galaxies? And kind of you keep tweaking that until you get something that reflects the large scale structure of our own universe. You know, you want a similar distribution of small galaxy clusters and large galaxy clusters. And that's a way we've been using simulations to narrow out different, or narrow down our idea of what the properties of dark matter might be. And where I'm going with that is that those simulations predict dark matter as what we call cold dark matter. You know, it's lower velocity dispersion. It's not very, and then versus hot, which would be a really high velocity particles moving around. Because if they're too high velocity, you're not going to form galaxies. And so we've been using these large scale simulations to narrow in on the properties of dark matter that will reproduce the universe as we see it.
So that's in another angle to perhaps rule out certain candidates so that we can focus on the most promising one for detection. Speaking of very fast moving particles, we have a question about neutrinos. So is there any matter that neutrinos interact with, and could they interact with dark matter? Is there a channel that would allow that?
Yeah, so let me start with neutrinos' interactions with other standard model particles. So they do have weak force interactions. So they take part in nuclear processes. So in something like beta decay, you actually emit an electron antineutrino. And then the reverse process can happen where a neutrino smacks into something and triggers a nuclear reaction. So then in terms of interactions with dark matter, it is possible that dark matter is made up of what we call sterile or right-handed neutrinos. And so the idea is that this is an extra flavor of neutrino, but unlike the other flavors, it does not have weak force interactions. And it is possible, depending on some properties of neutrinos that we haven't yet determined, it may actually be possible for one of the active flavors of neutrinos to spontaneously oscillate into sterile neutrinos and vice versa. And so this is a so-called neutrino portal. And there have been several generations of experiments that have attempted to detect sterile neutrinos. We haven't obviously made any definitive detection yet, but there are some, I would say, anomalous observations from certain neutrino experiments that can be interpreted as evidence for the existence of sterile neutrinos. And we're still sort of tracking those down and sort of combining the observations that we get from neutrino experiments with dark matter experiments.
That's very exciting. At least we have some channels to explore. Talking about larger scales, we have a question about not dark matter, but dark energy and the expansion of the universe. So our attendee asks, the expansion of the universe, what role does dark matter play in the acceleration of the expansion of the universe?
Well, I would say that it's not, well, the role it's playing is the same role that ordinary matter plays, which is it contributes to the expansion of the universe, but not to the accelerated expansion. If you have a universe that is dominated by matter, then Einstein's theory of general relativity predicts that the acceleration, it'll be a decelerating universe. And so really you need dark energy and not dark matter to get the acceleration that's been observed. But certainly to get all the details right, to get how fast the universe is expanding, say at the time when the cosmic microwave background formed, we know that we need the amount of dark matter that we think is out there in order to match those observations to the predictions.
Thank you. So that would be for a dark energy discussion, more than geared towards dark energy rather than specifically dark matter, but it's still an interesting question to explore the dark sector as a whole. We have a question here about not the dark sector, but rather dark life forms. So that's a very interesting question. Could there be life forms composed of dark matter, similar to the life forms composed of baryonic matter?
Well, I'm glad somebody asked that, because if you had asked me that a few years ago, I would say, no way. But then I thought about it a little bit more and I realized, well, maybe there is a way. And so I actually, with one of my graduate students, we wrote a paper that was kind of inspired by that question. And you see, it's very difficult because if you want to have dark matter life forms, then you need a pretty complex dark sector. It has to have chemistry, like in the standard model. And if it has all that, then you would expect that dark matter is really going to be very strongly interacting with itself. As I said, that might be okay. But we know other things. Like Jeremy told us, the dark matter halo is extending out way farther than the baryonic visible galaxy. And so we know the dark sector can't be exactly like the standard model, or the two things would just coincide with each other. And so the way we figured out is if you have a sort of mirror of the standard model, so everything's the same as in the standard model, except the two can't talk to each other except gravitationally. You could still get it to work if the temperature in the mirror sector was somewhat lower than the temperature in our visible sector. And it turns out when you look at structure formation in a model like that, it can happen that even though the dark sector is very strongly interacting with itself, it doesn't all collapse down to a disk like in the visible galaxy. Most of it remains in the halo. There will only be some little clumps, some maybe dwarf galaxies made of this mirror sector, where you could have dark stars forming and possibly dark life forms. So I think it's possible, but probably if there are such dark intelligent beings out there, they're much less numerous than us visible ones.
I have to say it makes a great plot for a Marvel movie, though. You have something like, you know, Thor, the Dark World, where there's this dark sector and these dark beings. And I think some of the terminology that we use kind of spurs that on.
So would we be dark? Would we be the dark sector to them, though? They wouldn't be able to see us just as much as we can't see them.
Interesting, that does make great sci-fi plots. I suppose we choose our names also in astronomy for somewhat aligned with that. Now we have a question that's a bit more applied towards direct detection, and it's actually quite technical. It asks, how does liquid xenon help to detect dark matter if dark matter does not interact with regular matter?
Okay, yeah, so that's a very good question. So I should probably explain that liquid xenon and liquid argon are two of the favorite, what we call targets for direct detection experiment. So basically we fill up a giant tank with this stuff and we put sensors all around the tank and we bury it deep underground and we put shielding around it. So basically the idea is that if there is some sort of very feeble interaction between dark matter particles and ordinary matter, you can get then what's either called a nuclear recoil or what's called an electron recoil. And so it's basically just like it sounds, a dark matter particle comes along and goes right through our overburden of rock and right through the shielding and everything and penetrates right into the detector. And then by statistics or by random chance, if we have a large enough detector and there's a large enough flux of dark matter particles, even if the probability of an interaction is very, very tiny, you know, that will still happen a certain number of times over the lifetime of the experiment if we wait long enough. And so when the dark matter particle hits an electron, it can actually kick it out of the atom. Similarly, when it hits a nucleus, it can put that nucleus into an excited state. And so then we get a tiny bit of charge and possibly a tiny bit of light produced in the detector. And so we can use the what we call the ionization signal and what's called the scintillation light, which we pick up using these sensors. And essentially the reason that we use xenon or argon is that they are noble gases, so they're not disturbed by all of the other chemical processes that tend to be going on. We can purify them quite well, and we can see their scintillation light. So when a particle does excite the scintillation, there are a lot of materials where that light is then absorbed by the material itself, or is very hard to see. The particular properties of xenon and argon make them very good for this.
Excellent, thank you. That must be a very sensitive detector to be able to pick up such a small effect.
Yeah, and it has to be very, very pure also. If in literally an entire ton of xenon or argon, we have one contaminant atom, that can mess us up.
This is why I am glad to work with computer simulations in theory. Now, we have an avid reader would like to have the link to the paper Professor Cline mentioned if you could put it in the chat, that would be perfect.
I did type it into the answer in the Q&A. Do you want me to put it in the chat also?
Is he answered? Yes. So thank you, I see it now. So perhaps in the chat as well, in case our attendee cannot find it in the answer. Thank you very much.
Sure.
So I'm also going to post in the chat. Oh, I think I just sent this to panelists. This is an article by one of my colleagues at University of Toronto about how to discover mirror stars. So it's not exactly mirror life forms, but it's mirror stars.
Yeah, ours wasn't really mirror life forms either. It's taking but you need structure and stars in order to have life. So it's like the first step.
Life as we know it, at least, yeah. I mean, we are sort of making some assumptions on what we call alive or what we consider a life form could be. You know, science fiction aficionados can come up with all kinds of just really radical concepts of life that exist in, you know, clouds or neural nets spread out in filaments throughout entire solar systems or things like that. So, yeah, we are sort of implicitly making some rather self-centered assumptions on what we think life is, and we're assuming that life is vaguely like us.
So speaking of fundamental assumptions, we have a question about just the existence of dark matter as a whole, right, which is based on our understanding of the laws of gravity. And so one of our viewers asks, what do you think about the emergent phenomenon theory from, I think, Dr. Verlinde? And so, or other models which claim that there is no need for dark matter. So could it be that our understanding of gravity is wrong, or are there pieces of evidence that are a bit stronger in favor of dark matter?
I'm not a big fan of Verlinde's particular theory. I think it's a bit vague, but I don't really know enough to criticize it. There's another theory, though, which has been very heavily scrutinized. It's called MOND, Modified Newtonian Dynamics. It was originally invented in order to explain rotation curves of galaxies without needing dark matter. But of course, we've seen, as I mentioned, you need dark matter also for cosmology. To get the cosmic microwave background right, you also need dark matter. Well, the people who worked on MOND also developed a relativistic version of it that would be able to try to address that question, and it's been tested. And it turns out that within this extended theory, it's called tensor vector scalar gravity, TEVIS. So it includes the MOND as a low energy limit. So if you test that theory against the cosmic microwave background, I think you find out that you still need something like half of the dark matter to be there in particles, and this TEVIS theory can explain the missing half. So that's really going against Occam's razor, and in my perspective is that's the best people have been able to do in trying to replace dark matter with modified gravity, and to me it's not very convincing.
So I should also say, from a particle physics point of view, there are some long-standing particle physics puzzles that actually had nothing to do whatsoever with astrophysics that were sort of hinting to us that maybe our standard model was incomplete. So these are questions like what we call the hierarchy problem, which is basically what keeps the masses of the different subatomic particles where they are, what makes gravity so much weaker than the other forces, what stabilizes the mass of the Higgs boson. And so forth. Things like in our fundamental theory of quantum chromodynamics, there's a parity violation parameter that is essentially always zero. Why is it zero? That's why axions were originally proposed, which then we later realized were dark matter candidates. So a lot of us really favor the idea of extra particles solving both the dark matter problem and other fundamental particle physics problems. And modifying gravity still does not really solve our particle physics issues.
One thing I like to remind myself when studying dark matter is just that, for hundreds of years, Newton's law of gravity held up and was the be all and end all of the universe. And it wasn't until observations got better and better that we saw it wasn't fully working at all scales. We came in, someone really smart came in and came up with general relativity, special relativity, and changed the way we looked at the universe. And then, as observations got better and better, we found this whole idea of missing mass, and we've invoked this idea of dark matter. And that's only happened in a pretty short time scale in terms of how long physicists have been working on problems. And so where I'm going with that is, I totally agree with my colleagues. This dark matter seems to be filling in the most gaps and explaining the most problems. But as observations get better, as our telescopes, as our detectors, everything gets better. I think it's good to keep an open mind, like some of these other theories. Again, they don't fill in as many holes as the dark matter idea does, but people should keep plugging away and keep working on that kind of stuff.
And that's a perfect point to wrap up our discussion, that this is very much research in progress, and that the laws of physics as we know them keep getting changed, either if it's a particle that we add to our models that we think is undetectable until, of course, it is, or if it is of a dark sector, which is still just so far away yet so close and could mimic some of the behaviors of baryonic matter. Or in this case, maybe even Einstein's, who seem sometimes untouchable, could be proven wrong in the next century or so. Thank you very much to all of our panelists for answering questions. Sorry if we did not get a chance to get to your questions. We had a flurry of very interesting and fascinating questions in the chat. Thank you very much for participating as attendees. This was a great evening. Thank you again to our panelists for participating.
Thank you, everyone. Thanks, Alex.